Welcome. Today, we'll tackle problem number 99, recover binary search tree. This is a fascinating problem that challenges our understanding of tree structures and algorithms. Let's dive in to explore how we can solve this step by step. In this problem, you are given the root of a binary search tree, or BST, where exactly two nodes have been swapped by mistake. Your goal is to recover the tree so that it once again satisfies the properties of a valid BST, without altering its overall structure. A BST is a tree where, for any given node, all values in the left subtree are smaller, and all values in the right subtree are larger. The input is the root node of the tree, which contains a value, a pointer to its left child, and a pointer to its right child. The task is to correct the tree in place, meaning you don't create a new tree or return anything. Instead, you directly modify the existing tree to restore its validity. Let's look at an example to understand this better. Here's the first example. The input tree, shown in its incorrect state, has the following structure. The root node has a value of 1, its left child is 3, and the right child of 3 is 2. This tree is not a valid BST because the value 3 is greater than the root, which violates the BST property. After the recovery process, the tree is restored to a valid BST. The root becomes 3, its left child is now 1, and the right child of 1 is 2. This satisfies the BST condition, where all left children are smaller and all right children are larger than their parent. Looking deeper into the explanation, the problem arises because the nodes with values 1 and 3 have been swapped. In the original BST, the root should have been 3, and its left child should have been 1. After identifying and swapping the misplaced nodes, the tree is restored to its correct structure. Now, let's examine another example to solidify our understanding. This time, the input tree is more complex, with the root node 3, its left child 1, and its right child 4. Additionally, the left child of 4 is 2. This tree also violates the BST properties, as the value 2 is incorrectly placed. After recovery, the corrected tree has the root value 2, with 1 as its left child and 4 as its right child. The left child of 4 is now 3. Notice that every subtree now satisfies the BST property. All nodes in the left subtree of 2 are smaller, and all nodes in the right subtree are larger. The misplaced nodes in this case were 2 and 3, and swapping them restored the tree. This highlights the importance of identifying the two incorrect nodes and swapping only their values while keeping the overall structure intact. Now, let's consider the constraints and edge cases to understand the problem's scope. The problem comes with several constraints and edge cases to keep in mind. First, the number of nodes in the tree can range from 2 to 10,000, so your solution needs to handle very large trees efficiently. Node values can range from -2 to the power of 31, up to +2 to the power of 31-1, meaning the tree can contain both negative and positive integers. Additionally, it's guaranteed that exactly 2 nodes are swapped, and the input tree is otherwise a valid BST. The tree structure must remain unchanged during recovery. Key edge cases include a minimum size tree with just 2 nodes, large trees with misplaced nodes deepen the structure, and trees containing negative values. There are no duplicate values, ensuring that each node has a unique value. With these constraints and edge cases in mind, you're ready to approach the solution. To solve the problem of recovering a binary search tree with 2 misplaced nodes, we first consider a brute force approach. The intuition here is based on the fact that an in-order traversal of a binary search tree produces a sorted sequence. By performing an in-order traversal, we can collect all the nodes in a list. Then, by comparing this list to its sorted version, we can identify the 2 nodes that are out of place. Once identified, we simply swap their values to recover the tree. The steps are straightforward: traverse the tree in order and store all nodes in a list, compare this list to the sorted version to find the misplaced nodes, and finally, swap their values. However, this approach has some drawbacks. Its time complexity is O(n) log n due to the sorting step, and it uses O(n) space to store all the nodes in a list. While it works, it doesn't leverage the tree's structure efficiently, making it less optimal. To improve on the brute force method, we can use an optimized approach that identifies the misplaced nodes during a single in-order traversal, without requiring extra storage for all nodes. The key observation here is that the in-order traversal of a binary search tree should yield values in non-decreasing order. If 2 nodes are swapped, this order will be violated at most twice. By detecting these violations, we can directly identify the two swapped nodes. During traversal, we track the value of the previous node. If the current node's value is smaller than the previous node's value, it indicates a violation. The first violation helps us identify the first misplaced node, and the second violation points to the second node. The process involves initializing variables to store the two swapped nodes and the previous node, performing the traversal to detect violations, and finally swapping the values of the identified nodes. This approach is much more efficient, with a time complexity of O(n) and a space complexity of O(h), where h is the tree height due to the recursion stack. With Morris traversal, the space can even be reduced to O(1), as we will discuss. The optimized in-order traversal approach is not only efficient but also has several advantages. It avoids the overhead of extra storage and leverages the tree's inherent properties for an elegant solution. An alternative to this method is using Morris traversal, which achieves O(1) space by temporarily modifying the tree structure during traversal. Instead of relying on the recursion stack, Morris traversal sets up temporary links between nodes to perform an in-order traversal without additional memory. The process remains similar. We detect violations in the in-order sequence and identify the swapped nodes. While this approach is highly space efficient, it comes with its own trade-offs. The implementation is more complex, and modifying the tree structure, even temporarily, might not be desirable in certain scenarios. As such, while Morris traversal offers an interesting variation, its added complexity often makes it less appealing compared to the recursive approach. Given the options, the chosen strategy for solving this problem is the optimized in-order traversal with O(h) space. This approach strikes the right balance between simplicity and efficiency. It directly utilizes the binary search tree's property to detect violations in a single traversal, making it both intuitive and easy to implement. While Morris traversal achieves O(1) space, its complexity and the need to temporarily modify the tree structure make it less suitable for this problem. The key insight, or the aha moment, came from realizing that the in-order traversal of a BST should always be sorted, and any violations in this order directly point to the misplaced nodes. While the recursion stack in the optimized approach can consume O(h) space, this trade-off is acceptable in most scenarios, especially given its simplicity and readability. Overall, this method delivers a clean and efficient solution without unnecessary complications, making it the ideal choice for recovering the binary search tree. To solve this problem, we're tasked with identifying and correcting two misplaced nodes in a binary search tree, or BST. Recall that in a BST, the left subtree of any node contains only nodes with values smaller than the node itself, while the right subtree contains only nodes with larger values. If two nodes are swapped by mistake, this key property is violated. Our goal is to restore the BST property. The approach we're using here is the brute force method. It involves performing an in-order traversal of the BST to collect all the nodes in a list, since in-order traversal naturally visits nodes in ascending order for a valid BST. Once we have this list, we compare it to its correctly sorted version, which allows us to identify the two misplaced nodes. The final step is to swap the values of these nodes to fix the tree. Let's break the algorithm down into steps. First, we perform an in-order traversal to collect all the nodes in the tree. This involves visiting the left subtree, the current node, and then the right subtree, ensuring the nodes are visited in what should be ascending order. Each visited node is added to a list, which we'll use for further analysis. Next, we identify the misplaced nodes by comparing this list to its sorted equivalent. Any two nodes that disrupt the sorted sequence are the ones that were swapped incorrectly. After identifying the misplaced nodes in the list, we can correct the BST by swapping their values. This step is straightforward but powerful. It restores the BST property without altering the tree's structure. By swapping only the values, we preserve the relationships between nodes in the tree. To understand why we use in-order traversal specifically, recall that it visits nodes in ascending order for a valid BST. If two nodes are misplaced, this order will be disrupted at exactly 2 points, making it easy to locate the issues. Comparing the collected list of nodes to its fully sorted version is effective because the list is already mostly sorted, with only 2 values out of place. This minimizes the work needed to identify the errors. Finally, swapping the values of the misplaced nodes ensures the BST property is restored. The positions of the nodes remain the same, so the tree structure is preserved, and only the incorrect values are corrected. To implement this approach, we rely on specific data structures. First, we use a list called nodes to store references to all the nodes visited during the in-order traversal. This enables direct access to the nodes later when we need to swap their values. Optionally, we can also create a separate list containing just the values of these nodes for comparison purposes. Let's break this process down further. In step 1, we perform an in-order traversal starting at the root of the BST. This involves recursively visiting the left subtree, then the current node, and finally the right subtree. Each node visited during this traversal is added to the nodes list. In step 2, we extract the values from the nodes list into a separate list called values. This list represents the node values in the order they were visited. By creating a sorted version of this values list, we can compare the two lists to identify mismatches. The two mismatched values correspond to the misplaced nodes. Once the misplaced values are identified, we move to step 3, which is swapping the values of the corresponding nodes. Using the nodes list, we locate the actual nodes whose values need to be swapped. By exchanging their values, the BST property is restored. Now let's analyze the complexity of this approach. The time complexity is primarily determined by the in-order traversal, which takes O, n, and the sorting operation, which takes O, n log n. This results in an overall time complexity of O, n log n. The space complexity is O, n, due to the storage of the nodes list. There are a few edge cases to consider. In the case of a single node tree, there are no misplaced nodes, so the algorithm should terminate without making any changes. If the misplaced nodes are adjacent in the in-order traversal, the algorithm will still correctly identify and swap them. For a degenerate tree, which resembles a linked list, the in-order traversal still applies, and the algorithm works as expected. These considerations ensure the robustness of the solution. Here, we start by defining the structure of a binary tree node using the treeNode class. Each node has a value, a left child, and a right child. Then we have the solution class, which contains the main method recoverTree. This method is designed to restore a binary search tree where exactly two nodes have been swapped by mistake. To identify these nodes, we initialize three variables, first and second to keep track of the swapped nodes, and previous to help in detecting violations during the traversal. Previous is initialized to a tree node with a value of -infinity to ensure that it is smaller than any node value in the tree. Inside recoverTree, we define a helper function called inOrder, which performs an in-order traversal of the tree. This traversal is crucial because, in a valid binary search tree, the in-order sequence of node values should always be sorted in ascending order. The function first checks if the current node is null and, if so, simply returns. Otherwise, it recursively traverses the left subtree. As the traversal proceeds, we compare the value of the current node with the value of the previous node. If the value of previous is greater than the value of the current node, it indicates a violation of the BST property, meaning that these two nodes may have been swapped. For the first violation, we store both previous and the current node as first and second, respectively. If a subsequent violation occurs, we update only the second node to the current node because it represents the most recent anomaly. After handling the violation, we update previous to the current node and then proceed to traverse the right subtree. Once the traversal is complete, the first and second nodes will represent the two swapped nodes. Finally, we restore the BST by swapping the values of these two nodes, effectively fixing the tree. This approach ensures that the BST is corrected in a time-efficient manner without requiring additional space for storing the nodes. Here, we begin the implementation by defining the basic structure of a binary tree node with the treeNode class. Each node holds a value and has references to its left and right children. Next, in the solution class, we declare three variables, first, second, and previous. These will help us identify the two nodes that have been swapped. Initially, first and second are set to null since we haven't identified the swapped nodes yet, and previous is initialized to a tree node with the smallest possible integer value. The recoverTree method is the entry point for the solution. Its primary goal is to restore the binary search tree by first identifying the swapped nodes through an in-order traversal. Once these nodes are found, their values are swapped to correct the tree. The in-order traversal is essential because, in a BST, the in-order sequence of values should always be in ascending order. Now, after identifying the swap nodes through the in-order traversal method, we swap their values to fix the tree. This is done by temporarily storing the value of the first node, assigning the value of the second node to the first, and then setting the second node's value to the previously stored value. Moving into the in-order traversal method, we see that it uses recursion to perform an in-order traversal of the tree. If the current node is null, it simply returns. Otherwise, it first traverses the left subtree. Then, during the visit of the current node, it checks if the value of the previous node is greater than the value of the current node. This condition indicates that the nodes are out of order. If first has not been set yet, it is assigned to previous, and second is updated to the current node. Finally, previous is updated to the current node, and the method continues by traversing the right subtree. This process ensures that we identify the two swapped nodes while maintaining the correct traversal sequence. In this first example, the input tree has two adjacent nodes swapped, nodes with values 2 and 3. Starting the in-order traversal, we initialize 3 pointers, previous set to -infinity to represent the smallest possible value, and first and second is none to keep track of the two nodes that need to be swapped. We begin with the root node, 1. Since the left subtree of 1 is none, we return and compare prevval with the current node's value, which is 1. There's no violation here, so we update previous to 1 and proceed to the right child, node 3. Comparing prevval, which is now 1, with 3, we see no issues and update previous to 3. Next, we traverse the left subtree of node 3, reaching node 2. Here, we compare prevval, 3, with 2 and detect a violation, since 3 is greater than 2. We identify the first node to be swapped as 3 and the second as 2. After finishing the traversal, we swap the values of these two nodes, restoring the binary search tree property. After swapping the values of nodes 3 and 2, the tree is successfully recovered. The structure now looks like this: 1 is the root, with 2 as its right child and 3 as the right child of 2. This demonstrates how the algorithm handles a simple case where the swapped nodes are adjacent in the in-order traversal. Moving on to a more complex example, we have a tree where the swapped nodes are not adjacent. The input tree has 3 as the root, with 1 as its left child and 4 as its right child, and 2 as the left child of 4. Notice that nodes 3 and 2 are out of place, violating the binary search tree property. To fix this tree, we again start an in-order traversal with the same initial setup, previous as -infinity, and first and second as none. Traversing the left subtree of the root, we visit node 1. Comparing prevval with 1 shows no violation, so we update previous to 1. Next, we process the root node 3. Comparing prevval, 1, with 3, there's still no issue, so we update previous to 3. Moving to the right subtree, we reach node 4 and compare prevval, 3, with 4. Again, no violation, so we update previous to 4. Finally, we traverse the left child of node 4, which is node 2. Here, comparing prevval, 4, with 2 reveals a violation, as 4 is greater than 2. We identify the first swapped node as 3 and the second as 2. After completing the traversal, we swap the values of these two nodes. The recovered tree now has 2 as the root, with 1 as its left child, 4 as its right child, and 3 as the left child of 4. In the third example, we have the simplest case, a single node tree. The input tree contains just the node with value 1, so there's nothing to swap. Starting the in-order traversal, we initialize previous, first, and second as before. Since the left subtree of the node is none, we return and compare prevval with 1. There's no violation, so we update previous to 1. The right subtree is also none, so we complete the traversal. Since no violations were detected, no swaps are needed, and the tree remains unchanged. This example highlights that the algorithm can handle edge cases gracefully, ensuring no unnecessary operations are performed on already valid trees. The time complexity of the solution for recovering the binary search tree is O(n), where n represents the number of nodes in the tree. This is primarily due to the in-order traversal of the BST. In an in-order traversal, we visit each node exactly once, and the recursive calls ensure that both the left and right subtrees are processed. This traversal accounts for the O(n) time complexity. During the traversal, comparisons are made to detect the swapped nodes, and each comparison is an O(1) operation. Since these comparisons are part of the traversal, they do not add any additional overhead. After identifying the swapped nodes, their values are swapped in constant time, which is an O(1) operation. Therefore, the traversal step dominates the overall time complexity, making it O(n). Now, the space complexity of the algorithm is determined by the recursion stack used during the in-order traversal. This space usage depends on the height of the binary tree, denoted as h. The maximum memory required corresponds to the depth of the recursion, which equals the tree's height. For a balanced binary tree, the height is approximately log n, resulting in a space complexity of O log n. However, in the worst-case scenario, such as with a skewed tree where all nodes are aligned in a single path, the height can be equal to n. In this case, the space complexity becomes O(n). Importantly, as no additional data structures are used, the recursion stack is the sole contributor to the space complexity, which is why it is expressed as O(h). To understand the efficiency of this solution, let's compare it to a brute force approach. A naive method would involve performing an in-order traversal to collect all the node values in a list, sorting the list, and then conducting a second traversal to overwrite the node values based on the sorted order. This approach would have a time complexity of O(n plus n log n plus n, which simplifies to O(n log n), and a space complexity of O(n), due to the additional list used for storing node values. In contrast, the optimized solution avoids the need for an extra list and sorting. By detecting swap nodes during the traversal itself, the time complexity is improved to O(n), and the space complexity is reduced to O(h). When analyzing different cases, we see that in the best and average cases, typically when the tree is balanced, the height is log n, leading to a space complexity of O log n. The time complexity remains O(n) across all cases. In the worst case, with a skewed tree, the height is n, and the space complexity increases to O(n), though the time complexity remains O(n). Finally, let's look at the mathematical proof for these complexities. For the time complexity, during an in-order traversal, each node is visited exactly once, and a constant amount of work is performed on each node, such as comparisons and updates. This makes the total work proportional to the number of nodes, resulting in T(n) equals O(n). The swapping of values between two nodes is an O(1) operation, which does not affect the overall complexity, keeping it at O(n). For the space complexity, the depth of the recursion stack is determined by the tree's height, h. In a balanced tree, the height is O log n, leading to a space complexity of O log n. In a skewed tree, the height is n, which results in a space complexity of O(n). This breakdown confirms the algorithm's efficiency in both time and space usage. When working on problems involving binary search trees, one common pitfall is failing to recognize and leverage the unique properties of a BST. For example, an in-order traversal of a binary search tree always produces a sorted sequence, and ignoring this can lead to solutions that are unnecessarily complex or redundant. Another frequent mistake is mishandling edge cases, such as trees with only one node, trees containing duplicate values, or cases where the entire tree is invalid. These scenarios can break your solution if not accounted for properly, so always test for robustness. Additionally, mixing traversal logic is a concern. This happens when you attempt to identify misplaced nodes during traversal but forget to preserve the correct relationships between parent and child nodes, leading to incorrect swaps. Lastly, modifying the tree without validating which nodes are actually misplaced is a risky approach. Always ensure correctness of your findings before making changes to the structure of the tree. Space complexity is another critical consideration. Using extra space unnecessarily, such as storing all nodes in a list during traversal, can lead to inefficiencies, particularly with large trees. In-place solutions are not only more efficient but often preferred in interviews. Speaking of interviews, it's essential to prioritize clarity when explaining your solution. Start by discussing the properties of binary search trees and how they relate to the problem before diving into the code. Interviewers value your ability to demonstrate understanding of the structure. It's also worth noting that optimized solutions, especially those achieving O1 extra space, are highly favored. While solving the problem, walk through small examples with visible issues like a 3-node tree with swapped children to illustrate your approach. Be ready to discuss trade-offs between brute force and optimized methods in terms of time and space complexity. Lastly, practice both recursive and iterative solutions, as preferences can vary between interviewers. Some may focus on the simplicity of recursion, while others might emphasize the control and stack management in iterative approaches. Understanding related problems can deepen your grasp of the concepts and broaden your problem-solving toolkit. For example, problems like binary search tree iterator and kth smallest element in a BST involve traversing the tree in specific ways, while validate binary search tree challenges you to enforce the BST properties. These problems not only reinforce your understanding of BSTs but also introduce techniques that are transferable to solving recover binary search tree. Additionally, exploring alternative approaches can help you understand their trade-offs. A brute force method, for instance, involves performing an in-order traversal, storing nodes in a list, and then sorting that list to identify the misplaced nodes. While simple to implement, this approach uses O(n) extra space, which can be inefficient. On the other hand, the two-pointer method optimizes in-order traversal by keeping track of misplaced nodes using two pointers. This approach runs in O(n) time and O(1) space, but it requires careful management of these pointers to ensure correctness. Another advanced technique to consider is Morris traversal, which allows you to perform an in-order traversal without using recursion or a stack. This approach is highly space efficient, achieving O(1) space complexity, but it comes with its own challenges. The implementation is more intricate and prone to errors, particularly because it modifies the tree structure temporarily during traversal. While this can be a powerful tool for solving the problem in an optimized way, it requires a thorough understanding and careful debugging to get right. Understanding these trade-offs between simplicity, efficiency, and implementation complexity can help you choose the right approach for the problem at hand, whether you're solving it in an interview or a real-world scenario. Great job! We've summarized the key points and approaches to solving this problem. Remember, mastering tree algorithms is a valuable skill for coding interviews. Thank you for joining, and I'll see you in the next lesson. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!